This is Binary Defense Without Privilege, which is maybe kind of a lame name for a talk, but this is actually the most people I've ever had turn up to one of my CircleCityCon talks, so thank you for coming, and I appreciate that this is the last talk of the day, and everyone's probably a little bit hungry at this point. So it is going to go a little bit shorter than 50 minutes, so you'll get out with plenty of time for dinner. So who am I? I am Steve Vittitoe. I work for Google on the Project Zero team, and I've been playing CTF for about 5 years now with the Samurai CTF team. I started this team about 5 years ago, and we compete frequently, so we compete probably once a month in a big CTF. So this year, like we just did DEF CON qualifications, we'll be going out to Vegas to compete in DEF CON CTF. My background personally is in binary exploitation and reverse engineering. So a lot of this talk centers around looking at things defensively with that sort of a offensive mindset. So I come from an offensive background, and for the last year or so, I was trying to think about how I would stop myself in this game of capture the flag. So a lot of this was born out of capture the flag experience. And this is my third year at CircleCityCon, so I've made it every year so far. I don't want to break this streak. More or less, you can think of this as a capture the flag strategy talk. And some of that may relate to real world things, and some of it may not. Your mileage may vary, but either way, you're going to come away with hopefully a few more tools in your bag to help defend things that need to be defended right away, right now. And the sort of scenario that we have with these attack defense CTF games is that you are not root, you are not privileged. You have the ability to change a binary. You can change a 1 to a 0 or a 0 to a 1, but you don't have things like source code. You don't have a vendor to support you. So right away you're thinking about old code that is no longer maintained by a vendor, no longer supported, but still must absolutely run, and it's critical to run. And you only have a short time frame. So this is going to be like in a scenario where you're under active attack. So you know people are exploiting you, and you know that you're in a hostile network, and you can't turn the stuff off. Right? It's not an option to turn this off. So the game of CTF presents this in a really, really succinct way to play with the attack and defense ideas here. So the central question that I'm asking is, what can we do without root, without source, with the short time frame in a hostile network where we can't turn things off to defend a binary? And there's a number of things to go into, but I think probably the easiest thing to do would be to look at it like a real example. So all these attack defense CTFs are all different, right? No two CTFs have the same set of rules, which is, number one, kind of frustrating. Number two, a real good opportunity to grow and adapt as the environment changes. So from last year at DEF CON CTF in Vegas, the services were all launched under XINetD, so everything worked over standard in and out. And they were launched under a seccomp sandbox, so they were actually pretty well defended for you already. And you had the ability to modify the binary and the environment in which the binary ran. But you couldn't do anything else, right? You didn't have root on the box. You couldn't set up like a network filter. You couldn't put the thing behind a firewall unless you became creative. Caveat, your mileage may vary with these strategies. By far the best solution, if you can do it, is to actually find the bug and fix it. So if you're being exploited by a Stack Overflow and a length is bad, fix the length, right? That's the best, most succinct way to go. And if you can do that faster than anyone else, that's sort of the best scenario to be in. Unfortunately, software is complex, and we don't always know where all the bugs are, right? So we're going to get exploited with something, and we may not know how that exploit works or where even the vulnerability is. All we know is that people are breaking in. And there may be more than one way to get in, right? So this is one thing that I've really enjoyed about CTFs as they have evolved, is that one binary does not equal one bug anymore. One binary equals 5 bugs or 6 bugs, and the binary might change on you in the middle of the game. So you have to adapt to these as well. And some of these strategies that we'll be talking about are really easy, like there's super trivial things you can do to defend something, and some things are a little more complex. So you might have to invest a bit of time in reversing parts of the binary to know if you can even apply one of these defensive strategies. And a good case in point here is when you think about what a compiler does to source code, right? A compiler's job is to make your source code run as fast and as lean as possible. So it's going to take up the smallest amount of space, it's going to run in the fastest amount of time, and anything you do to change that is probably going to run in more space and take more time. So how can you actually go into that sort of scenario and apply that working against the compiler in this case? So here's a kind of a simple example. Just a warning, this talk is going to contain assembly code and C code, and if you're not familiar with it, I apologize, but it's here, and I'll kind of try to explain it as we go through. But basically, how would you defend this Stack Overflow? So there's only 5 lines, so basically we have a call to put, so we're going to print a string that says overflow me on your terminal. We're going to move a stack variable into EAX, pass that to a function called gets. So gets is get string, and if you ever use gets in a C program with GCC today, GCC will complain to you saying, no, don't use get. Horribly insecure function to use. So as a vulnerability researcher, you see gets, you're like, hey, that's great, I can overflow something, because there's no bounds checking on gets. It will read data until you give it a new line, or null. Have to look up the details for that one. But the point is that there's a fixed size buffer for gets in this case. A 32-byte stack variable represented by EBP plus S. So that's 32 bytes on the stack that we're going to read in any number of bytes that we want. So we can blow right past that stack buffer. So you're given this binary, and you could see how you might attack it, but how would you defend it? What would you do here? Any ideas? This is interactive. You got to like hand up. I don't have any carrots or prizes or hats. I don't. But if you have any ideas, what do you think? Well, these instructions here are sort of the root of the vulnerability, right? So if we know that these are what's causing the problem, can we replace those with something else that, has the same kind of functionality, but isn't vulnerable in the same way? So this is sort of my first thought when I look at this, is can I have this do something different that won't go past 32 bytes on the stack? And if you were looking at this from C, right, if you had C code for this problem, and now you could write C code for this, you do puts and then it gets, it's 2 lines. But real-world binaries are more complicated than that. You can't always take a binary back to C code. In C code, you would probably do something like a scanf, right? So you'd replace that gets line with a scanf %31s to limit your string to 31 characters. It's 32 bytes in the stack. You have to have a null character in at the end for 32. And then you just recompile the patch binary and put it out there. So you don't always have source code, right? And especially in CTFs, you don't have source code. So decompilers can get you close to a lot of this. If you run hexarrays decompiler on a binary, you'll get something that almost compiles most of the time. And with a bit of hand-holding, you can probably get something that compiles and is very close to the functionality of the binary. But it's not perfect. It's certainly viable, and it's a strategy we have used for simple binaries. The other thing you can do in this space, which is more recent, is what's called binary lifting. So you take the underlying architecture, in this case would be x86 or x64, and you lift it to, like, not C code, but the intermediate representation that a compiler would use. So you can lift x86 code to LLVM IR, intermediate representation, and then that's text, right? So you can patch that text and recompile the IR code. And that's a lot more rigid in like how LLVM IR works at the assembly instruction level. And there's a really good public project from Trail of Bits called MC-Sema, or Mixema, however you want to pronounce it, that will do this for you. It'll take x86, give you LLVM IR, and then it can write abstractions and Clang around that LLVM IR to patch the binary for you. But speed matters, and getting this stuff correct is important. So maybe there's something else we could do, right? So we could do an inline patch here. Take those 11 bytes, replace them with something else that gets the functionality pretty close. It doesn't have to be exact. It just has to pass the polling test in a CTF, or has to work for a normal user under most circumstances in like a real-world scenario. So here would be like a small assembly patch that we could replace. So we push a byte 3, so that's 2 bytes. Pop that into the EAX register, so EAX is now 3. We're at 3 bytes for that. XOR EBX, EBX. set EBX to 0. So basically, what I'm trying to do with this assembly code is build up a call to read. I want to read 31 bytes from standard in. So I know that to do that, I have to have EAX set to 3, which is the system call number for read. I have to have EBX set to 0, because that's the file descriptor for standard in. And I have to have ECX set to my length, which is 31 in this case. And EDX is the fourth argument, needs to be set to the pointer on the stack where we're going to read. So to do all of that takes 13 bytes. It's so close, it almost fits, but not quite. And this is what I mean when I say you're battling the compiler for space, right? So the compiler can do the call to gets in 11 bytes. I can hand jam assembly in 13 bytes, but it's not going to fit. So this patch cannot apply to this binary. Similar techniques can work other places, but when you get into very, very small, like if you have a bug that is due to one instruction, you can't easily patch like 1 or 2 bytes. So you get into this concept of I'm going to have to not patch inline, but I'm first going to have to jump somewhere else. So I would replace this like push 3 pop EAX with a jump to a different location in the code. And that would be a location where I could put some more code. So it's like a trampoline, if you will, or a detour option. And this increases the complexity. You can automate the deployment of it to find these locations to put code. But maybe there's even something more generic we could do. Maybe there's even something we could do that doesn't require us to know about the bug in the first place, right? The fastest to defend wins. So this is a cool little trick that we've been playing for years in CTF, which is it's a Stack Overflow, right? So you got to think about how Stack Overflow works. If you want to exploit the Stack Overflow, you go past where your buffer should be, and then you start corrupting other things on the stack. And the most commonly used thing with this is the saved return pointer. So the saved return pointer tells, when you execute the return instruction, says where do you go back to? What is the next instruction executed by that binary? And if you can write to that, you can control what's executed next. Well, what if you never return? What if that return instruction never is executed? Suddenly, your corruption is meaningless. You've corrupted memory, but I don't care. I'm never going to use it. So we have in 5 bytes, right? So we can do XOR EAX, INC EAX, those are 3 bytes, and then an int 80 for 5 bytes to just call the system call for exit. So now this is only going to work in a narrow circumstance, right? Like your binary has to exit after it's been done, which means your corruption has to be more or less in main itself. So it's only useful when execution does not need to continue. But you don't have to know the bug to apply this patch, right? You can say, like, there's a bunch of stack buffers here, it's complicated, we're not going to return. We're just going to exit. So you can push that out quicker than other teams. And if someone else is able to automate an exploit or build an exploit fast, you're going to be patched before anyone else. Patched, right? You're going to be defended. Patching would actually be a proper, it's really ugly here. So you can actually do this in IDA Pro really easily. You can pull up like the example function prolog where you return 0 into EAX. You do a leave instruction and then a return instruction. So we want to exit before the return. We've got plenty of space there. So basically we could patch that B80000 to be 31C040CD80. And you can assemble that right into IDA Pro, just assemble right over that function. Say, generate me a diff file, and then apply that diff to the binary, and that's automated within a second. So that's sort of like the first cheap and easy attack defense CTF hack is don't return. The next one is, so we've got stack overflows, you have heap bugs as well, right? So we had a lot of these in DEF CON, and these are more and more common with real-world software. So the CTF attack defense binaries tend to mimic real-world software, so you have parity between the type of bugs you find real-world and in CTF. And one of the more common ones to find real-world these days is a use after free bug. So you have some object, you use it, you free it, and then you're able to use it after it's freed. And in between the time it's freed and when you use it the second time, you put something else there in that same memory space. Well, what if you never free objects? What if you just hold on, everything you allocate, you never get rid of. You can't use something after it's free if you never free it. And so this was a very simple observation that we had, and it's a very, very easy patch to apply. And in fact, it effectively defended one of the bugs in one of the 6 DEF CON CTF services. So it had a use after free bug. It was dynamically linked. All we did was replace the linker when it would look up free. We changed that to A to I. So it's A to I is a C function. It has the same number of characters as the word free, and it has the same parameters, has the same number of arguments, and it's not going to crash if you give it a bad argument. So A to I takes in an ASCII string, and it turns it to a 32-bit integer. So no crash. Free is now gone from the binary, so no more use after free bugs. And that worked, right? We didn't know where the use after free bug was, but we patched it with this technique. So there's lots of these sort of generic defensive opportunities when you have a binary that is dynamically linked. And in fact, the organizers really want you to move away from these generic defensive opportunities at DEF CON this year. So next year, they've claimed there will be no dynamically linked binaries. Everything is statically linked. So free is actually inside of the binary itself, and you have to at least reverse engineer the binary enough to find free to get rid of it. So back in this simple example with gets, at the top of that function, there's usually going to be something like a standard function. So you have, like, you save off your frame pointer, you push EBP, you move ESP to EBP, and then you subtract from ESP to give yourself space on the stack. Well, these constants are picked to minimize the amount of memory use. So that hex 48 here is picked by how much stack space that function claimed it needed when it compiled. We can change it. So we can change that hex 48 to like a F0, as long as it's still 4-byte aligned. And then after we have more room on the stack, we can change where local variables are inside of that stack. So that EBP plus S instruction, that S is a constant, I think it's like plus 2C. We can change that to be plus or minus D0 now. So if anyone looking at gets to overflow it, right, you're going to have an offset to know how far to get to your return address. You've got 32-bit stack buffer, you've got your saved frame pointer, and then you have your return address. So that's going to be what? 40 bytes in. So at 40 bytes, you'd put your return address. Well, now suddenly we've moved that buffer, right, 200 bytes further up the stack. So your offsets are all different. Now this is something that's really just going to annoy an attacker, right? Because you can repeat the return address as an adaptive technique, as an offensive defeat to this defense. But what we're trying to do is survive this 3-day window, right? So we're applying just enough mutation to frustrate things so that we can survive longer in a hostile environment. And the sort of the fundamental principle of all of this is the more variance, the more mutations we can introduce into a binary, the more assumptions we can break about the exploits that have been written for that binary. For example, who was here for the last talk? Elvis's talk. Yeah, it was a fantastic talk, right? So now he had a stack buffer, but what if that stack buffer moved with every image that was released? Right, so that would be something you'd have to think about how to defeat that. Well, could you repeat it? Would it be on the same offset? You can have, just as like genetic populations are affected by disease differently, you can do the same thing with a binary. And this is sort of like the most basic intro way to do those kind of things. And just as we have stack and heap overflows, we can do the same thing, the same trick with heaps. So you have malloc of some amount. It'll run just fine if you malloc 10 bytes more, 100 bytes more. So basically, if you have this malloc hex 80, all you have to do is find that push hex 80, change the hex 80 to a larger constant, and that's it. It's a 1-byte patch, and it will frustrate the heck out of anyone trying to do heap growing with your binary. You don't have to know anything about it, right? You just know that there's an allocation there. It's this size. We're going to give it more, and so long as you know the heap is functional in the way you would expect the heap to be, it should be able to survive this mutation. The trade-off is really only that you get a little bit higher memory usage, which I don't know. I take an extra 100 bytes of memory usage to help frustrate the 0-day attack. So that's sort of it for the binary patching. Everything else that I'm going to talk about is dealing with the environment in which you run these binaries, or what I'm calling environmental defenses. The first one is it was actually on all of the DEF CON binaries. They had alarm calls. So an alarm call is it's a system call that will cause the SIG alarm to be delivered to your process after X number of seconds. So if you did alarm 3, you could expect to receive a signal to your process after 3 seconds. And this means that if you exec a shell, like if you exploit a binary, you get a shell, that shell goes away after 3 seconds. So it kind of limits the amount of time that you can be on an exploited system. It's trivial to defeat, right? If your shellcode does a SIG proc mask or another alarm call, will replace the current alarm. If you do alarm 0, it will remove the alarm. And even if you don't have the option of running shellcode, if you get into a shell, you can exec this Python statement. Exec will not fork, so you're running on your same process. Python-c to run this string. You're doing signal alarm 0 and then execing a new shell after that doesn't have an alarm pending. So we actually wrote a little wrapper around this and as part of this Gatekeeper project. So there's a link here, SamuraiCTF Gatekeeper, and there's a sub-project in there called Alarm. And if you ever want to run a binary and have it terminate after however many seconds, you can run it as alarm, number of seconds to run, and then the rest of your arguments. So we've kind of tried to build up this pipeline of what defensive measures we can apply to a binary by execing them in a pipeline. So alarm is the first one in this pipeline that we would usually use. So back to this gets example. IDA had this in pink, right? So pink is sort of a code color saying that it's coming from the GOT table. So the GOT table means that gets was actually looked up from libc, and when it's called, it's dynamically resolved to libc. There is a trick with LD preload, which is an environment variable. You can say LD preload is equal to some library, and any symbols exported from that library are what gets looked up from these GOT resolutions. When the loader tries to look up gets, it will look at your library first, hence the preload. So we can provide our own implementation of gets. Again, this doesn't work for statically linked binaries, but for dynamically linked binaries, this is a really, really good way to go. It doesn't require knowing assembly. You can write C code to patch a binary, and this is kind of what it would look like. So you've got the C code on the right. Might be a little dark. You can ignore the init bit at the top, but down at the bottom you see we have gets, and it just does a syscall to read. Basically the same thing that patch did in one line of C. If you want to try this on your own, you have a GCC line to get you started. So you can compile it that way. That will take gets.c and generate gets.o. And if you run this sample overflow me program, so we run BOF, it'll say overflow me, you give it a long string of A's, more than 32 A's. And then it says stack smashing detected, so this is actually compiled with canaries in. But if we run it with our LD preload, this same code here, you say overflow me, you give it a long string of A's, well, it never reads more than 31 of them. So it doesn't overflow anything at all, so it just returns just fine. So you can mitigate that by replacing vulnerable APIs with your own, which is kind of cool, right? So if you know that the compiler is going to plan at you for having gets and you can't patch out gets in the binary, you can give it your own. I should talk about that init bit at the top. So up here we had init, extra FDs, and then we loop through 255 times opening dev null. Why would we bother doing that? That's kind of a weird thing to do. You run your binary, open dev null 255 times. And the idea behind that was to break weak shellcode. So we noticed that we were getting exploited with shellcode that was assuming things about our binary. In particular, they were assuming that the binary had never opened another file handle. An example of weak shellcode would be this here, where you open a flag file, you read from file descriptor 3 into buff, and then you write buff out to standard out file descriptor 1. Well, the read is assuming that the flag was opened into file descriptor 3, because file descriptors are open sequentially, right? So you've got 0, 1, and 2, standard and out and error. So the next open should be on file descriptor 3. But in our binary, we LD preloaded, and it now points to dev null. So you've just read dev null that you thought was flag. So it forces you to actually pass the return from open in shellcode to your system call to read, which makes your shellcode more complex and a little bit bigger. It also means that you can't use 8-bit registers, so you can't use AL. You'd have to at least use AX in this case, which incidentally breaks a lot of the Metasploit shellcode because it wants to have a small amount of space for shellcode, so it uses 8-bit registers. This is why we opened it 255 times to force the wider register width. So these are just like stupid little tricks, right, that we can do to make things more difficult. If you're using Metasploit shellcode, it will break because it's making some assumptions. This one was really cool. I was so upset when this didn't work out at DEF CON this year because they ran inside of a sandbox already. We couldn't make these API calls, but the idea behind this is that you don't have to be root to ch root. So you can have a binary as a limited user ch rooted into its own directory, and you don't have to have any privilege to do that. And this is all because of this wonderful, wonderful thing called the unshare system call, where you can unshare namespaces from your process. So in this particular one, you unshare clone fs, and then you can make a ch root call. And this has actually been a really big source of bugs in the Linux kernel and Linux setuid binaries that are assuming that the file system is set up in such a way that it couldn't be ch rooted without privilege. So there was one in Ubuntu that I think Tavis Ormandy found that like the crash reporter was exploitable by this ch root bug. And other sandboxing techniques can come from the same idea of unsharing namespaces. So we found that we could disable network access entirely. We could disable forking. We could stop spawned processes from killing outside of that sandbox. And we implemented it all in a really, really robust way and couldn't use it at DEF CON, so we open sourced it, which you can download. It's kind of like a Docker Lite, you could think of it as, where you have our ch root environment that will allow you to limit these different things coming into a binary. There's also another little technique here that can be used if unshare is not enabled in your kernel. So it doesn't have to be there, right? In fact, it's not there on like some embedded devices these days. It's possible to fake sch root. And you can do that by LD preloading, so that when a binary calls fopen or fread, those get called into a fake ch root fopen or fread, right? So this has been released publicly for a while. There's a really good wiki on it on GitHub, fake ch root. And it's actually really, really easy to detect either this fake ch root or the ch root through unshare. All you have to do is look at the inodes on your directory. So if you pop a shell and you're trying to figure out if you're in a ch root, you can do ls lai to get the inodes. And if the inode of your current directory and your parent directory are the same on the root of your file system, you're in a ch root. Yeah, so unfortunately that one didn't work out. This one did. This one was totally effective at DEF CON, and I think we were one of 2 teams that were using it. iNotify is a API in Linux that allows you to receive callback notifications on file system events. So you can say, I want iNotify on the flag file when it's been opened, which is a really useful thing to know, right? Who opened my flag file? So you can get like open, move, delete, modify, and a few other APIs that are available on the man page. We only used it for open. And we can actually build a generic defense around this, right? So if we're running as a service user, we iNotify on the flag notification that the flag file has been opened, and we can kill the process that opened it before the flag has been read, well then they can't read the flag file. So it's a bit of a race, right? So you're running in one process, the exploited process is running in another, and you have to race this notification coming back and forth. But it is actually very effective if you've popped a shell. So popping a shell, right, you do cat flag, it forks, cat is loading, it's going to open the flag file, it's going to read the flag file into memory, it's going to send it through a terminal back out to you, right? So all of that takes time, and we found that we can actually beat cat flag from a shell with an iNotify watcher. So that's really cool because it stops like this generic shell. If you pop a shell on our box and you cat our flag file, you get killed before you ever get a notification about the flag being read, before it ever comes back to you. Unfortunately, if you do this really, really fast, so I'm going to cat flag 100 times a second, The one problem with this is that we don't know which process caused the event to trigger. We don't get a PID back. So the only thing that we could think of to do to create a defense around it was to just kill everything. So we have I notify listening, we get a notification, we say, burn it down, and kill every process that we possibly can, except ourselves. And if you happen to have a team that's spamming cat flag to you, and the puller comes in and it gets hit at the same time, well, then you kill the puller along with the person trying to cat your flag, and you lose SLA points, so service level agreement points. This is all open source as well, so our iNotify is open source. We ended up backing off this due to the SLA loss during the game, and what we did is we hooked it up to Slack. So we had like SSH tunnels galore that would come back to Slack notify when we got exploited on a binary to know that our patches were ineffective. So we had some real-time situational awareness from this, which was pretty cool. The other thing we wanted to do was build in network filtering to some of our services. So we're not root, right? We can't do like TCP dump. We can't run an IDS. We can maybe put a process in the middle. So replace our binary with something that filters traffic for us. And here's an example that we came up with. So we set a flag file to the flag is defcon foobar. We set EXPR file to my password is defcon, and we can match regular expressions here, right? So we're matching uppercase, lowercase on defcon, and we have a more complicated regular expression there, hack the planet. And then all we do, we have the same pipeline, right? So we do /regex, which is our program that will filter the output, EXPR, the input file with regular expressions to filter, and then we'll launch a shell. So everything after this, after the regex command, is running through our filtered code. So we can echo hello, we can say who am I, we can see that there's a flag file. As soon as we go to cat the flag file, it matches the third line, defcon, right, because the flag file has defcon in it, and then the process gets killed, right? So, or we actually display a cheeky little message back, sorry Dave, I can't allow you to do that first. So if you wanted to go the other way, right, then you pipe sh through regex, instead of having regex exec sh. So you can filter both input and output with the same program. Unfortunately, you don't really know what kind of environment you're going to come into with an attack defense CTF, so we needed to have a way to do this sort of thing that would work on binaries that open their own socket as well, which can present a little bit more of a challenge. And what we built was something that was basically like SOCAT. So SOCAT, you can do TCP listen, you open a socket, and you can say, and forward that to this other host over here. In this case, we're going to use localhost. And what we'll do is we'll patch the constant number for the service port in the binary. So if it's listening on 1234, we'll change it to 1236, and then we'll start our filter program on 1234 and filter bidirectionally inside of there. So there's a separate fork of our whole Gatekeeper project that is a monolithic build. Everything runs inside of one binary, and it's got a whole lot more complicated command line options. But it will allow you to do network filtering on binaries that open their own network sockets. So that's kind of cool. Here's a link to the regex that will work as part of a pipeline, and a link to the monolith. I want to check that out. There's a lot of code there. I think there's probably several thousand lines of C code to implement all of this. Okay, so while we're on the topic of network filtering, a lot of times the organizers are assuming you're not able to effectively determine who's connecting to you. We actually found this wasn't true. We could figure out who is connecting to us. All we have to do is call get peer name on the socket coming in. So we could, for an XINetD binary, right, standard in, out, and error are actually all a socket. So if you call get peer name on 0, you can get the connecting IP address, and it's not randomized in some games. Some games are like double natted, and you can never really tell. They're always changing. This wasn't the case for at least one of the attack defense CTFs we played in. So we can get peer name. We can create a blacklist. For XINetD, there's actually an environment variable that will set the client IP address for you as well. And we found that it was actually a really good idea to always block localhost. And like, why would localhost be connecting to you? And what this is shell code from other teams exploiting service A, redirecting locally to exploit service B to skip the PCAP that you get from the switch. Right? So they encrypt it over the shellcode from service A and then redirect to service B so that they miss your network filter, so you can't steal their exploit. So if you block it, then you block that whole level of attack, and they have to come at you from the remote interface, or you'll get PCAP for them again. Although sometimes they might find a way to get around that, like if you exploit to 127.1.1 instead of 127.0.1, and you've only blocked 127.0.1, that sort of thing. We wanted to have a way to capture those exploits, or maybe change this so that we would always capture the PCAP from a service and not block the good stuff that was being protected over this encrypted channel. So we built our own PCAP logging tool that would go on top of this as well. So we effectively, when we receive data, build a fake network transmission on top of it. So you can run PCAP, give it a file name, and then run it in any command you want, and it will build a PCAP that represents input and output of that command. So just a little toolkit here. That's open source. You can see we run PCAP, foo.pcap, who am I, and Wriggle, the gentleman that wrote the tool, has a TCP dump example where you can see, the IPs are not set. They're both set to localhost, but you see the plain text is there. So any other follow-on tools that you have analyzing PCAP, this can then fit right back into. So while we're talking about environments, and there's a lot that we can do from an environment that affects a lot of sort of crazy things. The most simple thing that you can think of is environment variables, right? So the more entropy you have in your memory space, the better. You can randomize your environment variables at startup. So you can say set env foo equals blah, 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 blah. And then give it a long string. You can go like 20K if you want to. And then exec your process after that. So this is a very, very simple thing to do that helps to randomize your stack layout, stack addresses. It's very, very trivial to run that. I think the C code would actually fit on the slide if I didn't have the link to GitHub there. What else can we do? Okay, so that's sort of like it for the simple stuff. Now we're talking about forking. So have you guys ever run like a fork bomb on a system? Show of hands. No one's willing to admit to being malicious. 1, 2. So a fork bomb is a really nasty technique, especially when you're being penalized for uptime. So fork bomb says process A is basically while one fork, right? So process A becomes process A and process B, and then they're both in a loop forking. So process A and B becomes A, B, and then C, D. So then you have 4, and then 8, and 16. And you get, very quickly, you run the machine out of CPU, processors, and memory, and you can actually implement it in 6 characters in Bash. So this was not defended against at all at DEF CON for at least one of the services that still allowed the clone syscall. And indeed, we found people while one clone. And it would block the polar from coming in because we couldn't get enough resources to service the polar, right? We were effectively down. So you can block forking. If your binary doesn't have a need to spawn a process, please block forking because it is a very, very dangerously simple attack. So one way you can do it is from that unshare command. You can use seccomp to do it, or even simpler, you can use an rlimit command. So have you guys ever run like ulimit-a unlimited or ulimit-c to set your core file dump? Those are all variables that you can set from a shell. And there's a C system call, or there's a C API that goes along with that, where you can set your number of processes that can run under that same binary. Now it's system-wide, right? So if you set this to 5, you can only have 5 clients or 5 copies of that binary running at a time. So we created a little wrapper again, rlimit nproc, and you can set it to 0 and run sh. Now, sh is always forking. So if you do like an ls or a cat, right, that's forking to exec ls or forking to cat. You can't do that anymore. So you can see down here where we run head-n1. No, you can't do it. It's like denied, no child processes remaining. You've hit your limit of 0, right? You can't have any more. But you can use the shell built-ins, right? So if you want to do an ls, you can do echo star, right? So this is the sort of like attacker way to get around this. You can do read file with a shell line less than the file you want to read, and then you can echo that file back out. Or you can use the shell built-in exec to actually do the head-n1. So kind of a nifty thing to stop denial of service. It's not going to stop people from reading your flags, but if you do have a binary that doesn't fork, this is one of the first things I would consider disabling. And there are other useful things under rlimit as well. So you can limit CPU usage if you don't want to limit number of processes. So if you have a binary that has to fork, you can say you can't use any more than 0.1 CPUs. You can limit maximum file size. This one's pretty cool. If you have something that needs to write to disk and you don't want something to fill up your disk, right? You can say you can't write any more than 1 megabyte, right? These are all really, really easy things to do to a binary that just relies on the environment that they're running in. It's also useful to do umask 777 if the binary should never be writing any files. Then anything written will have no permissions and be of 0 size. So especially if you're inside of a CH root and do this, I don't know how you'd ever get out of that CH root. So tools to do CPU size and F size are also part of the gatekeeper pipeline. Okay, so I've got just a handful of more cool little things to show you. So this next one is got no bind. So we talked about how gets is looked up. So when you call gets, if it's never been called before, the linker says, I have no idea where this is. I've got to go look it up, and parses the libc elf header to find where it's at inside of libc, gets the address of gets, and puts it back into the got section of the binary. And this is a really popular place for people to leak information out of. So if you don't know where libc is, you can link something that's already been called, and the address of that will be in the got. So then you know where libc's at. And there's an environment variable, ld bind not. If you set that to 1, the linker will never store the addresses that's looked up in your got section. So if you link it, you're going to get all nulls back, right? You're not going to get the base of libc anymore. And it's super simple, right? You just have to know that that environment variable exists, and it will stop probably the most common ASLR defeat that there is. Likewise, along these same lines, if you have a program that's using a heap, most do, the heap has a whole bunch of configurable switches that can be set from the environment. So you can say malloc guard edges equals 1, malloc scribble, malloc protect before, and all of these change behavior, enable debugging behavior, enable the default values on the heap, put guard pages before your buffers. They completely change how the heap functions. So if you have an exploit that relies on buffers being laid out in a certain way, and you can change the behavior of the heap with an environment variable, you again come back to this point where you're breaking the assumptions of an exploit, right? So the exploit's assuming the heap works in this fashion. You've set an environment variable that forces it to not work in that fashion. You can maybe survive a 3-day time frame. So that's sort of the end of my cheeky little techniques that we can do generically. And there are sort of 2 classes that these fell into in my mind. One was things that you modified in the binary directly. You had the binary patching, a couple different ways to do that. We had the environmental changes, things that we could do that the program and linker will use to run your binary. You can affect the way all of those things work as well. And we definitely saw that you have more opportunity to generically implement defenses with dynamically linked binaries. And there's a large variance in effectiveness of these techniques, in large part due to how the rules of the game change, either real world or CTF. And some of these are very, very trivial to implement and will have almost no cost to implement, and some of them are a bit more time consuming and maybe ineffective depending upon how the game is run. So if you don't know the bugs, most generic defenses, you can think of them as an annoyance and a slowdown to attackers. Really, what you're trying to do is buy time to put in the reverse engineering hours to fix the bugs. So that's sort of the high-level overview of the techniques that we presented. There's probably about a half dozen to 10 more techniques that are actually in Gatekeeper itself. So I would encourage you to go back up to the root of that GitHub project. Everything is fairly well documented. There's testing for all of it too. And I'm around to answer questions about it if you have a play with it and end up with questions out of it. So hey, thanks for everyone who stuck around to hear the last talk of the day. And thank you to CircleCityCon for hosting me yet again this year. And we had a number of people on the team contribute to this project. So Chris Eagle, Dropkick, Zach Riggle, EBIP90, Hacks and League Room, and Kelson were all instrumental in creating this project. So big thank you to you guys when you go and watch this online. And I'm happy to take any questions you guys have about CTF, techniques in CTF. Question, yeah, go ahead. I don't know, is there Net Wars tomorrow? Tomorrow at 1? Cool. Well, so far what I've seen from the CTFs at CircleCityCon, they're a little different than like the attack defense or Jeopardy style CTFs. They're a little more accessible to people. So I wouldn't if you were confused or turned off by any of the content here, I wouldn't say like, don't participate in that CTF. They're all have their own sort of brand and theme to them. Any other questions? Yes. How do I feel about the what's this called? Pledge. Oh yeah, so pledge is yeah. So this was something that was proposed and sort of like implemented in a beta. The pledge syscalls. So you could say, I pledge that I will not use any networking APIs, and you kind of group the syscalls to their functionality. I think it's simpler than seccomp. Seccomp is kind of a pain to implement if you've ever tried doing that from C. But I don't think it provides you any different functionality than seccomp. In some cases, I think it leaves you a little more open to, you know, like, oh, I can hit that API that I didn't know about that was included in this pledge syscall, or I need to include this whole swath of APIs because I needed that one, right? So seccomp, you can say, I only need that one, and I will never call anything else but that one. So it's easier, but as with everything in security, right, ease and security are always at a tug of war. Other questions? Okay, thank you very much, guys.